As we continue to innovate and expand our offshore wind capabilities, understanding and addressing the challenges of fault management are critical to ensuring reliable and efficient energy transmission. In this video, I will present our work, Orchestrated Active Fault Management for Offshore Wind High Voltage DC Grids. The aim is to delve into the complexities of fault management, offering insights and solutions for creating a more resilient grid. My presentation includes 4 parts. First, I will introduce the background and motivations for my topic. Second, I will present the formulation of Orchestrated Active Fault Management OAFM method. Third, I will show the experimental study with the various types of faults to validate the effectiveness of OAFM. Finally, I will conclude my presentation. New York State has set a target to integrate 9 GW of offshore wind power into its grids by 2035. Achieving this ambitious goal raises 2 key questions. First, how can practical grid-forming controls in high-voltage direct current links be developed and deployed to enhance the transfer capability of gigawatt-level offshore wind power while mitigating security risks? Second, how can mass-ready and master HVDC grids be designed and operated to provide highly resilient connections for multiple gigawatt-level offshore wind farms to the main onshore high-voltage alternating current grid? AC master offshore grids with multiple terminal modular multi-level converter voltage source converter-based HVDC transmission technology can enhance transmission capacity, flexibility, improve reliability, and security. Under such conditions, offshore AC power grids will be power electronic device-dominated systems. Handling faults in such grids will be more challenging. Uncoordinated control during faults can increase the risk of triggering larger grid disturbance or even blackouts. First, all wind turbines and HVDC inverters inject massive reactive power to boost voltage, as shown in Figure 1. Those uncoordinated currents from offshore wind farms can monotonically increase fault currents. Excessive fault current can burn critical equipment, for example, offshore cables. It can also cause the faults to expand, for example, from single-phase to ground fault to double-phase or even three-phase to ground fault, or from a temporary fault to a permanent fault. Second, the active power transmitted by its VDC inverter will be significantly reduced if a fault occurs near the inverter, as shown in Figure 2. There will be a huge power mismatch between the power generated by the offshore wind farms and the power transmitted to the onshore power grids by HVDC inverters. As shown in Figure 2, the angle difference between the HVDC inverter and offshore wind farms increases monotonically, causing a loss of frequency stability. Therefore, frequency instability will occur due to the lack of coordinated power control between HVDC inverters and offshore wind farms. Third, offshore wind farm will generate power ripples and asymmetric faults. The oscillating power can intrude into the DC side of HVDC inverters, resulting in DC voltage ripples. So the question is how to manage the fault response to achieve orchestrated grid support. Our solution is Orchestrated Active Fault Management. OAFM is a programmable optimization problem that can incorporate customized objectives under evolving grid conditions. The basic concept of OAFM is as follows. First, considering the highly controllability of inverter currents, which means the currents of offshore wind turbines can be controlled for either the angle or magnitude. At the fault point, the fault branch current is equal to the sum of HVDC side and offshore wind farm side currents. Without OEFM, the relationship among the currents is shown by the dashed lines. With OEFM, the magnitude and angle of the offshore side current can be adjusted. The new relationship after adjustment is shown by the solid lines. It can be seen that the magnitude of both the total fault current and the offshore side current are reduced. which clearly shows the reduction of fault current contributions from offshore wind farms. Second, the power imbalance among HVDC inverters and offshore wind farms can be controlled in a coordinated manner to maintain frequency stability. The power mismatch can be calculated or estimated based on the rate of change of frequency of offshore AC grids, and then mitigated by adjusting the output power of offshore wind farms and HVDC inverters. Third, to suppress the effects of offshore wind farms' output power ripples on DC voltages of HVDC grids, the power ripples of offshore wind farms can be reduced with OEFM. Next, I will present the formulation of orchestrated active fault management. OEFM is a multifunctional method and aims to, first, minimize fault current contributions from offshore wind farms during fault ride-through. Second, minimize power ripples of offshore wind inverters. And third, provide orchestrated power control and frequency response. The schematic diagram, as shown in this figure, illustrates this process. The voltages and currents of offshore wind inverters and HVDC inverters are sent to the OEFM controller. OEFM generates the current and power references and sends back to offshore wind inverters and HVDC inverters. For the formulation of OEFM, it minimizes the weighted sum of three objectives. The weights can be selected, for example, by Pareto frontier to achieve better control performance. The first objective is the fault current contribution from offshore wind farms. The formula for F1 varies depending on the fault location. When the fault occurs at fault point 1, FP1, as shown in this figure, F1 is expressed in equation 1. When the fault happens at FP2, F1 is expressed as equation 2. The second objective is the power ripples of offshore wind farms. The ripples are calculated as the difference between the instantaneous power and the fundamental frequency output power of the wind farms. Here we minimize the average output power ripples of all offshore wind farms. The third objective is the system power imbalance. The power imbalance is calculated to adjust the power reference or output power of offshore wind farms, thereby reducing frequency deviation. The extreme of rate of change of frequency corresponding to the maximum balanced power at the beginning of the fault is used. The unbalanced power, delta PL, is shared by all offshore wind farms and HVDC inverters. OEFM has two types of constraints: device capacity constraints and coupling constraints. Device capacity constraints include safety current ratings for HVDC inverters and offshore wind inverters. This means that the current should not exceed the rated capacity of this device to ensure safe and reliable operation. Coupling constraints have two parts. First, network or tie-line rating constraints, and second, current constraints by non-zero sequence components. The second constraint is the power reference of HVDC inverters should not exceed their capacity. This ensures that the HVDC inverters operate within their safety limits and prevent overloading or damage. The third constraint is the nullification of zero-sequence currents. OEFM can be solved by the sequential quadratic programming method in a centralized manner, or distributed and asynchronous surrogate Lagrangian regularization to further speed up the calculation. The control schematic of offshore wind inverters and HVDC inverters is shown in these slides. In our test system, double-loop control-based grid following control is applied by offshore wind farms. Loop control-based grid forming control is applied by HVDC inverters as shown in the two figures respectively. For the offshore wind inverters, under normal conditions, the double-loop-based controllers are functioning. The inner loop current controller receives the current references generated by outer power loop controller. During faults, the outer loop controller is bypassed, and the inner loop current controller receives the current references generated by the OEFM controller. For the HVDC inverters, we directly change the power reference to adjust the output active power to maintain frequency stability. To further improve the performance of orchestrated active fault management, sequenced OEFM can be developed. This approach controls currents in the sequence domain. With sequenced OEFM, it can provide controllable negative sequence currents for protection without causing overvoltage in the healthy phases during asymmetrical AC faults and improve the performance in suppressing offshore wind power ripples. The sequenced OEFM has 4 objectives. The first 3 remain the same. The fourth objective is the negative sequence current magnitude. This objective is to provide allowable negative sequence currents. With the sequenced voltages and currents, the relationships among power, currents, and voltages are provided in this slide. To eliminate offshore wind farms' out-power ripples, we can directly calculate the positive and negative currents by setting their values to 0, as shown by the final equation of the slide. The constraints to sequence the OEFM are the same as the non-sequenced OEFM. Next, I will present an experimental study that examines various types of faults to validate the effectiveness of OEFM. This will provide evidence of how OEFM performs under different fault conditions, demonstrating its robustness and reliability. The studied system is an extension of the CRGRE HVDC grid and the CRGRE HVAC offshore wind farm benchmark system. It has 9-terminal HVDC grid and 3 offshore wind farms. 2 offshore wind farms, each rated at 1 gigawatt, are masked at the AC side. The third offshore wind farm, 600 megawatt, is connected to a HVDC inverter. The build test system is developed and compiled in RSCAD and simulated in real time with 2 RTDS racks. The OEFM controllers are implemented and executed on personal computers in real time. RTDS sends voltage and currents to OEFM controller. The controller runs OEFM algorithm in real time and sends reference back to RTDS once a fault is created. We conducted multiple cases, including balanced and unbalanced faults, to verify OEFM. On this slide, a balanced fault is triggered at 0.1 seconds and cleared at 0.4 seconds. The testing results without and with OEFM are shown in figures 1 and 2 respectively. Without OEFM, it can be observed from the results that: first, the wind farms contribute 1,100 ampere to the total fault current in magnitude. Second, the out-power ripple is negligible due to the balanced nature of the fault. With OEFM, it can be seen that the magnitudes of the HVDC inverters and the fault branch currents are controlled to the same. 3 optimizations are conducted. It takes 80 milliseconds, 100 milliseconds, and 20 milliseconds, averaging 66.7 milliseconds in the whole process, which means OEFM can output reference timely to achieve online control. On these slides, a phase A2 ground fault is triggered at 0.1 seconds and cleared at 0.4 seconds. The results without and with OEFM are shown in the 2 figures respectively. Without OEFM, offshore wind farms contribute to the fault currents with a magnitude difference of approximately 550 ampere. Second, the wind farm's power ripple is around 6.1%. With OEFM, the fault currents from the HVDC inverter side and the fault branch are controlled to the same. The current magnitude difference reduced to 0. The OEFM controller sends the reference values 3 times during the fault, which means 3 round optimizations. The average time is 54.3 milliseconds. The testing results validate that OEFM works in real time to reduce the fault current contribution from offshore wind farms. On this slide, a phase AB to ground fault is triggered at 0.1 seconds and cleared at 0.4 seconds. Without OEFM, as shown in Fig 1, offshore wind farms contribute to fault currents with a magnitude difference reaching 800 ampere, and the fault current contribution is about 50.4%. Second, the wind farm's output power ripple is around 40%. With the OEFM controller, the fault currents from the HVDC inverter side and the fault branch are controlled to have the same magnitude, and the magnitude difference reduced to zero. Second, the offshore wind output power ripple is reduced to 24%. OEFM controller conducts 3 times optimization during the faults, with each round taking average time 56.7 milliseconds. The double phase to ground fault also validates the performance of OEFM. To validate frequency instability mitigation capability, a 3-phase short circuit is triggered. The test system is operated near rated conditions to create possible frequency instability cases. The testing results without OEFM are shown in this slide. It can be seen that, first, after the fault is cleared, the output power of HVDC inverter increases gradually. The system oscillates significantly after 75 seconds. Second, the system's frequency deviates severely from the allowable value. The system loses frequency stability. When OEFM is activated, the system's response are given in the 2 figures. It can be seen that, first, the system's frequency is in the allowed range after the fault is cleared, and the system doesn't lose stability. From the change of frequency wind farm current references, we know that OEFM works to adjust the HVDC inverter and wind farm's output power to maintain stability. All the testing results validate the effectiveness of OEFM. The last part is the conclusion. First, OEFM is formulated as a programmable optimization problem that can incorporate customized objectives on evolving grid conditions. Second, OEFM can reduce fault current contributions from offshore wind turbines, suppress power ripples, and provide orchestrated frequency response. Third, OEFM can output reference values quick enough, around 60 milliseconds, for online dynamic controls. Thanks for watching.